In our pulley lab last week, we found the acceleration of the system experimentally, and we saw that that was significantly lower than if we used F net equals ma on the two masses and figured out the acceleration that way. So why? Well, we did not look at the pulley itself, and we haven't yet in this course considered the forces on that pulley or the energy associated with spinning the pulley. And now we will. And we would see that if we did think about this pulley in terms of it needing energy to accelerate, well, if there's energy going to rotating the pulley, there's less energy to the motion of the masses. So, to derive rotational kinetic energy, that is the kinetic energy of something spinning, not moving translationally in space, I'm going to look at this disk and consider rotating this small mass. This small mass I'll call M1 R1 of the entire disk. And I know that the kinetic energy equation is 1/2 mv squared, and I know that there's a relationship between V and the angular speed of the disk, omega. So I substitute that in, and I come up with this expression where I'm talking about one specific piece, M1. The R1 is the distance away from the axis of rotation. So that's the kinetic energy associated with rotating just that one piece. So if I wanted to find the kinetic energy associated with rotating the entire thing, well, I need to add up piece by piece by piece by piece, all of these together until I have all of the disk, and that involves a lot of calculus. So you can see here I'm adding up one piece that I called, maybe this is the piece where I called M2, and that would have been R2. And now another piece, so I have M3, R3, and so on. So I would have basically an infinite amount of terms that I'm adding up. But I know that this expression, this function where I add up mr squared, is defined. It's defined to be the moment of inertia for the specific object, whatever it is. And this is dependent on the mass of the object and the radius away, like each piece. So it's the configuration of the object. And it also, in this term remember we're solving for kinetic energy of rotation, the angular speed by which this thing is rotating also matters for this kinetic energy. So let's look at some application over on my other board. Also, I'll mention here, just like we talked about work and how that changed the total energy of the system, there can also be a work done by a torque. So I've mentioned many times the analogy between linear mechanics and rotational mechanics. Remember, the force could essentially be substituted for torque. Displacement could be substituted for angular displacement. So we have this same general equation for work, just with our rotation variables. So let's look at an example now. So if things are moving, we know that kinetic energy is present, but we also know that there's kinetic energy associated with rotation. So if I take a marble and I let it go, I know that this marble is probably going to be spinning something like that. So it would have two types of kinetic energy. The translational kinetic energy, 1/2 mv squared, and the rotational kinetic energy, where this marble has some value I that's not changing no matter where this thing is in space or how fast it's rotating. It's just some coefficient times omega squared, so how fast the thing is rotating about. If I took two objects, say a marble and a block, and they both have the same mass, and I put them up on a ramp, I could ask, well, which one would hit the ground first? Assuming that this block doesn't rotate, and maybe that there's very little friction between the two surfaces so that it's negligible, I would expect the block to hit the ground first. Consider the energy, the wall diagram here. This is the initial snapshot for both of the objects. When it starts out, all of the energy is in gravitational potential energy. There's no spring, there's no kinetic. But when we take our final snapshot, when both of these things are at the ground, well, here for the sphere, I have translational kinetic energy, KT, and I have rotational kinetic energy, KR. And since I started with 4 blocks, I end with 4 blocks because there's no energy going into or out of the system. Well, in the block's case, it's not rotating, so all of the energy is going to translational kinetic energy, which means at any point in time, this block has a larger translational velocity than our marble does. So we would expect the block to hit the ground first. What about, say, a hoop or a sphere, both of which we know are rotating? Both have the same mass, same radius, start off at the same height. So we need to look at the moments of inertia for each object, both the hoop and the sphere, and those can just be pulled from a common table or would probably be given to you in any problem that you solve. So the hoop is 1/2 or mr squared, sphere is 2/5 mr squared, and I move to the expression because it will look similar to this little diagram. So I start off with gravitational potential energy, and when I get to the bottom, or when the objects get to the bottom, they have translational kinetic energy, both those terms look the same, and rotational kinetic energy, 1/2 I omega squared. The only difference here is this I, which we have values for, and instead of calling this omega to get one velocity in this expression, I'm going to substitute omega in with V over R. I guess I call it capital R. So I substitute that in there, and I can start to simplify this. Over here I see an R squared, and I see an R squared there, because this will apply to both terms, so those will cancel out. And I'm left with 1/2 mv squared plus 1/2 mv squared, which is just mv squared. The m's cancel out. So the velocity of this hoop is the square root of gh. In the sphere's case, I plugged in the I here. Well, the r squares will cancel out. So I'm left with mgh equals 1/2 mv squared plus 1/5 mv squared. You add up these two terms. So the way I added them up, if you're unfamiliar with this method, I take this term and I multiplied it by 5 over 5. So it's just 1, it's not changing the value of the term. So this would be 5/10. This term I multiplied by 2 over 2. So that would be 2/10. And I get 7/10 mv squared. There's an m in both terms, so I cancel out the m's. And I move this term over to the other side by multiplying by 10 and dividing by 7. So my ultimate value for v is the square root of 10 over 7, or 1.2 square root of gh. So the velocity of this sphere is 1.2 times greater than the velocity of the hoop. We would expect this to hit the ground first. So that's rotational kinetic energy. You should be able to, after this video, look at an object like, any object could be given, but let's say maybe a disk on top of a ramp. Maybe the mass is given, maybe the radius of the disk is given. You should be able to calculate the velocity at the very bottom of the ramp, and other kinematic variables beyond that as well. Okay, that's all for now.